now I'm going to cover 5.3 all the way through the end. So, to pick up where you were with me before and went through the review, it was our review on vector scalars and Pythagorean theorem. So if you feel a little bit lost, there's another video posted on Edpuzzle. Please take some time to review it. If you know that will benefit you, but otherwise I'm skipping the review. Hopefully you got the notes from the book and you're good to go. Components of vectors. Okay, so when you talk about the Pythagorean theorem and you see the two components, the up component and the vertical and the horizontal component. These guys are completely independent of each other. Remember, this is completely affected by G, while the horizontal component usually is a constant. So every vector can be resolved into two components when they're at a right angle to each other, all right? So, and we call these components. So please write that definition down. The components are this. We call these components. This is the resultant. So this, the process of determining this is called a resolution. Process of determining this is a resolution. Probably write that down if you haven't already from the book. Okay, so if you chuck a ball into the air, you toss it to your friend, your buddy, whatever, or you shoot a free throw, that ball's path, the initial path, can be broken down into a vertical component and a horizontal component. We call this the y and the x component. Pictures and the x component. Okay? Obviously, that y-axis and the x-axis. Okay, so we talked about this. We tested the x-axis when we did the fan cart and the buggy, and we tested the y-axis when we did the free fall of the ball drop. So if you did not end up switching this to the y-axis in your lab, you got some really funky data. So we'll kind of reflect on that. So components of vectors, how do they affect each other? They don't. They're independent. That's the key. Projectile motion. Now let's talk about projectiles. The horizontal component. So we spent a chapter talking about linear motion. We spent part of a chapter talking about free fall and acceleration. This is constant. This is free fall. Okay, so this is going to be hugely important. So the definition of a projectile is anything shot through the air that's acted on by only gravity, and the caveat here, sometimes air resistance. Okay? Cannonball, stone throw, ball thrown, a spacecraft circling the Earth. All right, this is called a satellite, and it's constantly falling towards the Earth. That's what a satellite is. Okay? Again, satellite, cool little side note. These paths are really simple because you can just break them into the horizontal part of it, the path, and the vertical part of the path. We can even do this on video analysis. Count on it, it will be happening. Okay, when you roll a ball along the surface of the Earth, it moves constantly, just like the buggy, just like the fan cart. Constant rate. So this would be like that marking in your analysis. Okay. Now, if you drop the ball, it's going to accelerate. So this is just like the situation with the basketball. Every second you should have marked it, or every millisecond, it should have gotten greater and greater distances as it fell because it's accelerating every second. So, a horizontal is completely independent. It's repeated like 800 times. Completely independent. They don't affect each other. Okay? But many people find that hard to believe. Describe the component completely independent. So the downward motion of a horizontally launched projectile. So if I launch something horizontally, it's going to be the same thing as free fall. So what that means is if I throw a ball the exact same time you drop a ball, it will still hit the ground at the same time, because once it leaves your hand, the only thing acting on it is gravity. It doesn't matter how hard you throw that ball. I could throw a 100-mile-an-hour fastball. Not that I can, but I could throw this sucker super hard, and it would still hit the ground at the same time. It would just be farther away at the ground. So here's an example. A strobe light released the ball, and it took pictures really every second, and it marked it, and the balls ended up hitting the ground at the same time. And we'll be testing this in the class. Right? Kind of hard to believe, but we will test it. You can slow mode on your phone. Some of you, I'll pick one or two. But it does indeed fall at the exact same rate. It's hard to do it with a buddy just because you don't always release at the same time, and I have a mechanism that will. Okay, the horizontal remains constant. It is constant, while gravity acts only downward. So the acceleration is actually only downward, and the horizontal is just dependent on how far, like the harder you throw it, the farther it will land from the original point, but it will still fall at 9.8 meters per second and hit the ground. Either if I drop it here, straight down, or if I chuck it like a 100-mile-an-hour fastball, it'll land over here in the exact same amount of time. Okay, so that means when you're given a situation where you throw a 100-mile-an-hour fastball, you're going to have to calculate the time it takes to hit the ground. And then you can use that time to calculate its distance. All right, so that's where you're going to play in a couple different equations. We're going to talk through that in class. Okay, the ball moves at the same horizontal distance every increment, because there's no horizontal forces, maybe a little air resistance. So this path, we call it a parabola. Okay. So when air resistance is small enough to neglect, that curved path is generally perfectly parabolic. And my picture is not a good parabola. Okay. So if a cannonball is fired and a cannonball is held at the side and they drop it at the exact same time, which hits the ground first? Neither. They both hit the ground at the exact same time. Okay. So describe the downward motion of a horizontally launched projectile. Gravity is the only thing acting on it, so its downward motion will be parabolic, but gravity will pull it to the ground at the exact same speed, just in a different location on the planet. Okay, so what if they're launched at an angle? What if I launch them up? We're going to do this. Or launch them downwards, right? So like the rockets, a handful of you got to launch them straight up. What if we launch them at an angle? How is that going to affect it? Okay. No matter what angle, it's still going to fall at 9.8 meters per second. So it's just going to be a little bit closer to the ground. So it might hit the ground a little sooner because you may have released it a little lower. But once it's out of your hand, it's still going to fall. Like you'll take this is where VI, when we saw those VIs, if you actually throw it at like 10 meters a second, this is when this is going to play a role. But it doesn't matter what angle you throw it at, because it's still going to fall 5 meters in the first second, 20 in the second, 45 from the start in the third, and 80. Don't quote me on that. I'd have to do the distance equals 1/2 gt squared. Okay? So, but no matter what, it's going to fall the exact same distance. Just It's a matter of like how much distance it has to like cover. So if you throw it like upwards, it's going to have to free fall from whatever that original position it would have been in. So it's going to hit the ground a little bit later. So with no gravity, this sucker would go straight up. Again, shows you the distance here. So the sharper the angle that you shoot it, it's going to have less of a horizontal distance. And eventually, if you shoot it at a more flat rate or a more down rate, it's going to be closer to the earth. So to calculate it again, 1/2 GT squared. Okay. The top of the path, its vertical component shrinks to 0, and then everywhere else the velocity is greater. Okay. So here we go. Each time, notice the horizontal component stays the same and the vertical component gets smaller, goes to 0, and then gets gradually bigger because 9.8 meters per second squared every time. Okay? So horizontal ranges. This is where things are a little bit different. The greatest range is 45. If you launch something at 45 degrees, it's going to go the farthest. 60 and 30 will have an equidistant, and 75 and 15 will be equidistant, and we'll test this out as well. And that's just because of the distance from the ground that it has to travel to arrive to its final destination. Okay. So pretty much the same range is obtained for two different projectiles for the angles that add up to 90. So anything that adds up to 90, your distance will be about the same, which is why the max range is usually like 45. Okay, speed. Without air resistance, a projectile will reach max height at the same time. It takes the fall from that height to the ground. Okay, so if I throw it up in the air, it'll reach that speed, and then it will accelerate due to gravity. It'll hit the ground the same speed you threw it up at. Okay. We've talked about this in the past. Now, if there is air resistance, obviously, if you've played a sport outside, you realize like you have to adjust for the wind or the air. Okay, something to know. The longest time a jumper is airborne, no matter if they're moving forward or they're just jumping straight up, is about 1 second. So that's 1.25 meters, which is 4 feet. 4 feet is pretty significant to raise your center of gravity. Okay, practice question. Vertical acceleration is always g. 0 because it doesn't accelerate horizontally. What point does the path does a projectile of minimum speed at its peak? At the very top, it's 0. Okay, reflect on this. How far below? It's the same as in free fall. Okay, I'm not going to go over the practice. Well, I'll flip through the practice questions. You can work through them if you want. Pause before I show the answer. Pause before I show the answer. Feel free to jot these in your notes. Pause before I show the answer. Pause before I show the answer. Pause before I show the answer. There you go. Hopefully that helps.